All right, here we go with AP Physics 1, last test this cycle. So, as per usual, College Board only releases Form J, which is the operational form, the one that's taken by the most students. So if you had a different form, unfortunately, they don't release it. But those forms, sometimes people find different forms harder. They do have different cut scores, so you're not graded on the same scale as someone with this form. You're only graded on a scale of students with your specific form. So with that, let's look at Form J. So first we have a pretty typical momentum setup where we have a cart moving at some speed vc. Then the block lands on the cart. It's stationary in the x direction. And then the block cart system moves at some other final velocity. So this is a very typical momentum question where we have some sort of a system moving, and then we add some mass to it, and we need to figure out what happens later. So first, we want to sketch a graph of the magnitude of the momentum of the block cart system as a function of time. So it's important to read what we're graphing here. We're not graphing the speed of the cart, we're graphing momentum. And we know that if there's no external forces, which is true in this case, external being external to the block cart system, we know that the sum of the momentum in any given direction, so in this case the x direction, must be constant. It wouldn't be in the y if you're sort of dropping that block on the cart and the cart bounces to stop it vertically. So we're just looking horizontally. So we're conserving momentum in the x direction. So that allows us to just draw some sort of a constant curve there. Now we'll derive an expression for the speed of the cart after the collision occurs. And for our derivation, since it's a collision, of course, we're going to just use momentum conservation and use the fact that the sum of the momentum in the x direction is going to be constant. So that means that the momentum before has to equal the momentum after. So before the collision, we have a cart of mass mc moving at a velocity of vc to the right. And then we have a block of mass 1/5 m moving at a velocity of 0 horizontally, so there's 0 momentum there. And then after the collision, we have the cart and the block, which is a fifth of the cart's mass, moving as a combined object at some unknown velocity vf. So then we can just write mcvc is equal to 6/5 vf, because we added a fifth to 5/5. And then we see that vf is just going to be 5/6 of vc. And that should make sense qualitatively, because if you are adding mass to the system, in order to keep the same momentum, your velocity has to shrink by the same factor that your mass went up to get the mv's to equal each other. Now we want to derive an expression for the change in kinetic energy of the block cart system. So, well, we're wanting the change in kinetic energy, so we should use the expression for kinetic energy. So if we're finding its delta, we're just going to take the kinetic energy at the end and subtract the kinetic energy at the start to get the delta. Then for the final, we know that for the final state, we're going to use the total mass in our kinetic energy formula. And then in the starting state, we're just going to use the cart mass in our energy formula. So now we can plug in. So we solved for each of these things. So the total mass we said is going to now be 6/5 of the cart mass. And the final velocity is going to be 5/6 of the cart's initial velocity. And then we'll subtract off the initial KE. And now we get to have some fun with fractions. Although I do believe this is an acceptable final answer, just leaving it right here. So maybe I'd encourage that. So just kind of doing some fraction arithmetic here. I'll pull a 1/2 in front of the whole thing. So I'm going to have 6/5 times 5/6 times 5/6 times mcvc squared, and then subtract mcvc squared. And now that allows me to easily see sort of what my fractions will reduce to, because the 6/5 cancels with one of the 5/6. And then I might want to write 1 as 6/6 to make my subtraction easier. So then I'm just taking 1/2 of negative 1/6, which gives us a delta KE of negative 1/12 mcvc squared. And again, notice that we got a negative answer here, which makes sense because all collisions, except for elastic ones, lose KE to the surroundings. So if we get a positive answer, we probably flipped our subtraction sign or did the momentum wrong. So now we're going to consider the case where the block is dropped and collides again, but instead of the collision just happening instantly, there's this frictional force between the block and the cart. And we're going to indicate whether the X momentum increases, decreases, or remains constant. So we're really just saying, going back up here, what happens if instead of sort of an instantaneous collision, it's spread out over a longer time? And well, doesn't matter, because the block cart system is closed. So it's going to still remain constant because those are internal forces. Yes, it's very true that friction can take energy from your system, but this is friction between the block and the cart. So I like this as an action-reaction pair argument with Newton's third law. So the friction is internal to the system. So yes, it's true that the block will slow down the cart, but also the cart will speed up the block because forces are always equal and opposite. So the momentum lost by one block will be gained by the other. Thus, there's no momentum net change. Impulse is always equal and opposite. I'm sure there's other arguments you could use. It might just be as simple as saying it's a closed system, and if there's no external forces, then the momentum of a closed system remains constant. But I like this third law action-reaction pair. So in terms of scoring, for your 2-point graph, you probably get a point for each region. You probably get a point for it being constant before the collision, and then you get a point for it being constant, the same constant value after the collision. Interesting that that's worth 2. Then for your derivation, I would say that this is probably worth, out of the 7 points for 2 and 3, I'd probably say that this is worth 3. You get a point for momentum conservation. You get a point for recognizing it's an inelastic collision perfectly, so they stick together. And you get a point for saying the correct final answer. Then 2 points for this part, even though there's a lot more algebra. You get a point for a valid expression for kinetic energy change with variables. And then you get a point for a consistent substitution of your final velocity into that. And like I said, once you get all of the symbols in there, this rate here would probably be where I'd stop. Because there's no points for simplifying. That is a complete final answer. So it'd be out of 2. And then for your final 3 points, you get a point for a checkbox. And then maybe some point about recognizing internal forces. And then a point on justifying how that internal force relationship results in 0 delta P. So that's out of 10. Nothing strange on that at all. All right, now we got an energy conservation. We have a block that's sliding down a ramp, compresses a spring, and then stops. So the first thing we're going to do is draw some energy bar charts at each of the following points. So first, when the block is at the top of the ramp, then when the block is sort of halfway down the ramp, and then when the block is compressing the spring some distance, it's already drawn for us. So what is important for us here is that energy is conserved in this system because there's no friction. So we're just going to add to figure out how much energy budget we have. So I have 7 plus 3 plus, sorry, I have 7 plus 2 plus 3, which gives me 12 E0. So I know that I actually have 12 E0 as my total energy budget. So what that allows me to do is figure out pretty easily that I need to add to 12 each time. So first, when we're at rest on top of the ramp, that's pretty easy because it is just gravitational potential. So I am going to draw a bar that is 12E0 tall. For UG, and then K and US are 0. Actually, I think we want to draw this 0 bar. So we got 12, 0, and 0. Then for figure 3, we're at 6D. So there's actually something nice that happened in this energy chart. So we see that UG is worth 12 when it's 12 ticks above the bottom of the ramp, and it's at 2 when it's 2 ticks. So each tick actually represents 1 bar of UG. So if I'm 6 ticks up the ramp / 6 ticks down the ramp, this means that my UG is just going to be 6. E0. And also, my spring is not compressed at this time, so that means there's no spring energy. And then to make my budget work out, there's actually an equal amount of kinetic energy to get 6 plus 6 equals 12. So again, we can see this works out because my energy budget remains constant throughout the whole process. So then we're looking at a final state when the block momentarily comes to rest, so it maximizes the spring compression. So it says starting with conservation of energy, so we better use conservation of energy, derive an equation for spring constant K. So by starting with conservation of energy, we can state it however we want. I am just going to state it like the energy sum has to be constant. So at the top of the ramp, the only sort of energy that's going to contribute is going to be our gravitational. And then at the end, the only type of energy we will have is going to be the spring energy. Because I'm just going to set that as my 0 point of GPE because I can't go any lower than that. So GPE is equal to mgh. And spring potential energy is 1/2 k delta x squared. But neither h or delta x are given, so we have to figure that out. So first for our h, we can see that the block travels a distance of 12d down the ramp. So its height, just based on trig, is going to be 12d sine theta, because sine extracts the vertical components. And then for the compression of the spring, we'll come back to that. We're just going to see how many tick marks the spring actually compresses. Well, going back up here, we see that the spring is initially located at 1, 2, 3, 4, 5, 6, 7, 8 D. So at the 8D tick mark is when the spring starts. So we're just going to be compressed from 8 to 12, which is 4D. So the spring compression is just going to be 4D. We have to square that, being careful of parentheses. So I get 12 mgd sine theta is going to be equal to 1/2 k times 16d squared. So I get 12 mgd sine theta equals 8kd squared. Or canceling one of the d's and dividing, we'd get 12 over 8 mg sine theta over d is equal to k, or simplifying the fraction, k is equal to 3/2 mg sine theta over d. And we know that by unit analysis this works out because mg sine theta is a force and d is a distance. So a force by a distance is a spring constant, Newton per meter. So everything looks good here. Then we want to do this interesting graph. So we have to graph two things. First, sketch a line or curve that represents the total energy of the system from 8D to 12D. And we can do that first. That's quite easy. We said our total energy budget is 12E0. So that is going to be my total energy E. And then we want to sketch the gravitational potential energy from 8D to 12D. So we can sort of reverse this, because I know that 12D, my GPE is 0, and I also know that by MGH, it's going to be a linear dependence. So I'm just going to draw a straight line from 12D to where the GPE started. And we said one tick was worth one. One tick was worth 1 unit of GPE, so I am just going to do that. Because if the block slides 1, 2, 3, 4 units down, it is going to lose those 4 E0 units of GPE. And that happens linearly. And another interesting thing would be to actually ask you to graph kinetic energy, which is kind of related to part D. I thought that would be quite tricky. So you can think about what a kinetic energy curve would look like on this. So last, we want to indicate whether the speed of the block at 9D is greater than, less than, or equal to the speed at 8D, using the energy chart. So we know that based on our energy chart, all the energies must add up to 12E at all times. So notice there's absolutely zero issue at the 12D marker, because I see that I have 0 plus 12. I have 0 plus 12, which is going to equal 12. But I do actually have an issue at 8D, because I have 4 plus something equals 0. So my K curve would actually start at 8E0. And maybe I'll draw this in a different color. But then if I'm looking at 9D, I see that the GPE is going to be 3E0. And the EPE, or elastic curve, is actually not quite E0. It's a little bit less. It's actually 3/4 if you work it out. But this means that the kinetic energy should actually slightly increase to make your accounting go up. So what this means is that kinetic energy goes up, so the speed is actually going to go up. And if you graphed a K curve, it would actually peak and then decrease, so maybe something like this. Something like this maybe could be your kinetic energy. But again, that's sort of our justification using the energy curve, is that on the graph in part C, the GPE decreases by E0, but the elastic potential energy increases by an amount less than E0. So to make your budget work out, we need to make sure that difference in energy is made up in the kinetic. So the block will speed up, because the increase in spring energy was slightly less than the decrease in GPE, so there had to be that extra kinetic term to make it all work out. So now for scoring. This is out of 3. So I imagine this curve is a point, this bar chart is a point, and then your third point would be the sum is equal to 12E0. So 1 point for a split between K and UG for the 6D, 1 point for all of it in gravitational, and maybe 1 point for the sum always equaling 12E0. Now for our 4-point derivation, you get a point for starting for conservation of energy. You get a point for valid expressions for GPE and EPE. You probably get a valid point for substituting in for H and delta X, and then you get a point for the answer. Then for your 3-point graph, you probably get 1 for the labeled E curve. You get 1 for the labeled UG curve, and then you probably get 1 for the sum of E equals 12E0. So for it to be reasonable, that all 3 energies would add up to 12E0. But let's actually restate that. So I actually think they're going to change it to you get 2 points for the UG curve. So you probably get 1 point actually for the x-intercept, and you get 1 point for the y-intercept. That would be how I actually think they split it into 3. Then for your 2-point justification, you get a point for saying the speed is higher, and you get a point for a valid justification. All right, now for our lab question. Students are investigating balanced systems using this setup. the students have a spring scale of negligible mass that's fixed to one end of a uniform meter stick. They can hang this block from all these different holes, and they can use a spring scale for force. So this is definitely a balanced torque problem, because if you hang a block from some distance x from the pivot point, it's going to exert some downwards torque. And the spring scale over here is set at some distance of 0.5 meters. So we can write a pretty simple relationship. I'm actually going to write it down here in part B first. I let the equation guide my setup. I actually know that the torques equal each other. So the left torque is equal to the right torque. And what that means is that the force I apply to the spring scale times 0.5 meters is equal to the mg of the block times the distance x at which it hangs. So what that means is I need an experiment that's going to allow me to acquire f and x, because I know g and I want to solve for m0. So for my procedure, pretty straightforward. It even gave us that there's all these holes drilled into it. So we're hanging a block from one of the holes. We record the distance x from the midpoint. Use the spring scale to record the force required to balance the meter stick at each point. And to reduce uncertainty, repeat for multiple holes, recording the x and f each time. So now that makes our analysis pretty straightforward, because we said that 0.5 f is equal to m0gx, which tells us that f would be equal to 2m0gx. So we could just say our graphing technique is pretty simple. You just graph f versus x, and then the slope is 2m0g. So there's your analysis. Pretty straightforward. Since it's already linear, you just graph f versus x, and the slope is 2m0g, and then obviously solve for m0. So as long as you said that how the slope relates to m0g, you're good. All right, now for our new setup, we have the meter stick hanging from the wall, and we have quite the nasty equation to set up. If we actually had to derive this ourselves, we'd have to be very smart about the point we take the torques around, but that's actually done for us. We are given this fact that the tension force required to keep the meter stick at rest depends on the angle theta via 5/6 times mg divided by sine theta. So this means that our linear relationship is going to be ft as a function of sine theta on the denominator. And we already have ft and we have sine theta, so we just need to reciprocate sine theta. So that's what we can see here in this table. Is the reciprocated sine thetas. And then as per usual, I am not a point plotting expert. This usually takes me longer than any of the other physics in this class. So I did some off-camera mining, as I always call it. And here is our linearized graph. Notice it is scaled. And sine theta is unitless, so I didn't have to put any units there. So now we have to draw an appropriate best fit line. And here's a case where the y-intercept is going to be not 0. Not by, theory says it is going to be 0. But this data really shouldn't have a y-intercept of 0. If I try to draw a y-intercept of 0, it's not really the best possible line. But again, our best fit line should just be something that approximately gets half the data above and below the line. I think something like this does a better job of that. But again, there's a range. I'm also not the best of the best fit drawing. It just has to be reasonable. So here, notice I got 1 point pretty near the line and a couple. They're either just above or just below. And maybe I even would do something more like this. So then we're just going to analyze this to calculate the experimental value for the mass of the meter stick. So as per usual, especially since I am really bad at drawing best fit lines, I don't feel confident that I can necessarily get a great slope by hand. So I always go to our Lord and Savior Desmos graphing calculator. And we can just get our regression equation from that. So let's see what that ends up being. All right, so after checking Desmos, just running the linear regression, we get y equals 7.9x plus 0.39. And then our relationship to the best fit line and the quantity of interest, we were given that ft was equal to 5/6 mg multiplied by the quantity 1 over sine theta. So that means that if we look at the things that we graphed, ft versus 1 over sine theta, we see that the slope is just going to be what's in front. So the slope is 5/6 mg. So this means that the mass of the meter stick is just going to be 6/5 times the slope, all divided by g. And I use g equals 10 meters per second squared here and got 0.95 kilograms for the meter stick. So you're probably getting a range of values, especially if you did the slope by hand. But that is my experimental value. So again, there's a range if you did the slope by hand, but if you did regression, it's probably pretty close to that. And it also depends if you use 9.8 versus 10 for G. All right, points. Pretty straightforward. 2 points for part A. Did you vary? Did you record F and X? And did you do multiple trials? There's your 2 points. Did you graph a valid relationship and relate the slope to M0? There's another 2 points. Did you pick the right relationship to graph? That's a point. Did you scale your axes with units, plot the points, and draw a reasonable best fit line? If so, there's 3 points. Did you relate the slope of the best fit line to the quantity of interest? And then did you solve properly for a value of M? If so, there's your final 2 points in the lab question. And lastly, we got fluids. And this is actually a really straightforward fluids question. So we have a swimmer that holds a block at rest underwater, and they let it go. And it's given that the block accelerates upwards. So this is something where the block will not sink. Instead, it's going to float. And in a different scenario, they're in a saltwater tank as opposed to freshwater, which has a different density, but it is greater. And we're going to be interested in comparing the accelerations of the blocks in saltwater versus freshwater. So first we got to indicate which acceleration is bigger. And it is given that the salt water is more dense. So we know that, just for some diagramming out here, we know that the buoyant force is equal to the displaced mass by your object times g. So it's just the weight of the displaced fluid. And we know that displaced, the mass can be written as rho of the fluid times volume. So if we have a higher density fluid, that means that the weight that volume will be displacing is going to be bigger for this saltwater case. Because yes, it's the same volume that gets displaced, but you're displacing a more dense fluid. So you're going to have an increase in buoyant force. And buoyant force is the thing that's pushing the block up, and they're going to still have the same mg down because it's the same block each time. But due to that boost in buoyant force from the increased density fluid, the second acceleration will be higher for that reason. And I thought I did a pretty good job of coming up with an explanation that doesn't reference equations at all. So we know acceleration relates to net force. In both scenarios, the blocks are experiencing buoyant force and gravitational force. The buoyant force increases in scenario 2 because you are displacing a higher weight of fluid, but they have the same gravitational force. So if block 2 has a bigger force up, but the same force down, there's a bigger net force up, so it accelerates upwards faster. And now we're going to derive an expression for that acceleration. And it even tells us start from Newton's second law. So I'm going to do just that. I'm going to write sum of the forces is equal to ma. Then I always like to draw my forces as the things helping acceleration minus the things opposing. So we're given in this case that the block is going to accelerate upwards. So I know that there's some sort of upwards force that's going to be the net force, and then there's some gravitational force opposing. So for my net force, I'm going to write it's the buoyant force that helps minus the gravitational force that opposes. For the buoyant force, the general expression for buoyant force is rho GV, and then the gravitational force is mg. And then I'm just going to divide through by m to get rho GV over m minus g is equal to a, which is a correct answer, but I'm just going to clean it up by factoring out that g. So I'd get, just to see the dependency here, I would get v over m times rho minus 1 all times g. And I factored out the rho like that in the first term, so I could see that with an increase in density, you're increasing the positive term in the net force equation, so an increased density should cause the acceleration to go up, which is exactly what part C will ask us. Indicate whether the expression is or is not consistent. Yep, definitely is. 1, because I know I solved the problem right. But looking at the expression in part in part B, we see that notice that as the density increases, the positive term in the acceleration equation increases, which means that A increases. So that's consistent, because we said that the more dense fluid should result in a higher acceleration. So yes, they're consistent. The acceleration of the block is the difference between the two terms, the buoyant term and the gravitational term. The gravitational term is constant, but the positive buoyant term is proportional to density. So since acceleration increases as density increases, it's consistent, because we said that A2 would be bigger than A1. So now for a point breakdown. 1 point for a correct selection, so again this is out of 3. 1 point for the valid selection. 1 point for identifying both forces that are acting on the block, upwards buoyant and downwards gravitational, and then explaining that there would be a greater buoyant force in scenario 2, and thus a greater net force. So again, you can usually get these justification points without getting the problem right in the checkbox. Then for your 3-point derivation, multi-step derivation using Newton's second law, valid expression for buoyant force and gravitational force, correct answer. And then for our last 2 points, 1 point for a valid consistency argument, whether it is or isn't, and then a valid justification. So that gets you your 8 for your QQT. Overall, especially compared to some of the things we've seen in Physics 1 over recent years, yeah, this is pretty straightforward. So hopefully we're able to find some success with this. I know a lot of us were kind of nervous about fluids, but I thought this was a pretty straightforward fluids question. We didn't see Bernoulli at all. And I really like that we just had to compare the sort of buoyant forces and knowing that it was related to the weight of the fluid you displace. But yeah, pretty straightforward.